advocate at Zillas, where he advocates for the open source vector database Milvus. Prior to this, he spent 3 years in the industry as an applied ML researcher at Twitter and Meta, collaborating with product teams. Stefan holds a PhD from the University of Oxford and has published papers at leading machine learning conferences like NeurIPS and ICLR and ICML. He's passionate about generative AI and is eager to leverage his deep technical expertise to contribute to the open source community. Welcome, Stefan.
Okay, so just plug this in here, I take it. Okay, well, thanks everyone for coming. Glad to have you here, and yeah, thanks for the opportunity to speak at the conference, David and organizers. I'm from a company called Zillows, who are behind the most widely adopted vector database, Milvus. And so when we're doing events, we sort of have like a bit of a sort of, slightly gimmicky, enter like a star Milvus, enter a raffle, you win a prize. Unfortunately, I can't offer the the raffle today. I can only offer good vibes, but really appreciate if you scan that code, star us on GitHub, and check us out. I really appreciate the support. So I wanted to begin today by mentioning a fact, and I think it's like a very it's something that kind of like surprised me when I heard it, and that is that 90% of newly generated data in 2025 will be unstructured data. And so that's kind of like the motivation for our company Zillows and what we do. So our mission is to help organizations make sense of unstructured data via our vector database, so Milvus open source vector database technology. Just a bit about myself. So as mentioned, I'm a developer advocate for Zillows, which means I work completely on the open source side with Milvus. And so as a developer advocate, something I was only sort of became familiar with when I was starting this role. So my sort of like core responsibilities are to like bridge the gap between the developers and users. So I really love connecting with users. I love like hearing about what your use cases are, help you overcome any sort of like technical hurdles, give advice on how to prototype generative AI applications like semantic search. So do connect with me on LinkedIn. And I slightly changed my talk topic a bit from what might be in the program. So instead of talking about like a multi-agent system for analyzing your, say like your user forums or your user docs, I'm going to be talking about something very similar, and that is building a research agent to do the same thing. Okay, but before I go into that, just a few words about Milvus for those of you who aren't familiar. Or maybe I should just ask, so how many people have heard of Milvus? Okay, how many people have used Milvus before? Okay, so good. I see a few hands. Everyone's familiar with it at least. So I'll skip over this fairly quickly. So I think, I'll skip over these slides because, this is a search conference. So Milvus, it's the most widely adopted open source vector database. And when I say most widely adopted, we can like quantify that via PyPy pools, Docker pools, GitHub stars, number of forks. So that's something we're really proud of. And so the one of the sort of like the key points is it's built for scalability from the ground up by database and AI experts. So you can read those two research papers on some of the engineering going behind the distributed systems aspect of Milvus that make it so scalable. And so for time's sake, I'll just keep going. But just briefly to mention that so many large companies are using it every day in production for doing semantic search, RAG, agents for databases on the size of literally tens of billions of vectors, with still like very, in some cases, like sub 10 millisecond latency. And here's just like a few of our users. Okay, so I'm going to be talking to you about. Actually, before I do that, so one sort of like I think useful aspect of Milvus is that it has different deployment options. So when you're prototyping, you're obviously not at the 10 billion vector scale. So you don't want to be sort of like setting up an entire Kubernetes cluster. So we have Milvus Lite that runs in your Jupyter notebook, and that's what I'll be showing today. And then one step up from that, we have a Docker version that you can use for larger scale prototyping locally, also actually serving real traffic up to say like around the 100 million mark. And then when you really want to scale up, there's the distributed version, so fully distributed system, separation of concerns between the different nodes, and that literally scales to the tens of billions of vectors, and all open source. Okay, so I'm going to be talking to you today about how we built a very simple but effective research agent, which we call Deep Searcher. And as I'm sure like many of you were, so when OpenAI came out with Deep Research start of February, we were really inspired to, I guess, like build not really like a clone, but something that would sort of, I guess, like emulate some of the like the functionality. And so what exactly is like a research agent? How does that kind of like differ from a regular agent? Well, I mean, I think the definition of an agent is up for debate. So I guess like research agent, probably less well defined, but here are some of my sort of the common themes I could take going through the OpenAI blog announcement. And so the first one is an aspect of iteration. So to perform research, it seems like we should need to do multiple steps, learning to plan and execute a multi-step trajectory, probably need to do backtracking and reacting to real-time information, pivoting as needed in reaction to information it encounters. So for those of you who like have a bit of familiarity with this area, so that's like clearly talking about these reasoning large language models that have been trained with like these sort of like these reasoning traces to perform like a multi-step reasoning. A research agent, it seems like search is another big part of the definition. So OpenAI's Deep Research was trained using end-to-end reinforcement learning on hard browsing and reasoning tasks across a range of domains, and optimized for web browsing and data analysis. So it seems like a research agent should be able to do web browsing and be really sort of specialized in doing that specific type of tool usage. The third thing is reasoning. So, and these three aspects have a lot of overlap, of course. So OpenAI, they mentioned their Deep Research was fine-tuned, or it used a reasoning model fine-tuned on the upcoming, at the time, OpenAI O3 reasoning model, and leverages reasoning to search, interpret, and analyze massive amounts of text. So, and as you're aware, perhaps we've had like a few sort of breakthroughs in training reasoning models in the last couple of months with work by DeepSeek and others. Okay, so before I actually sort of like give a demonstration, go into the code, I think it's helpful to sort of just show like an architectural diagram. And it's like a really simple design, but it seems to work really effectively, I think, because of like the power behind the reasoning model. So instead of sort of like designing a really, sort of putting a lot of like different steps into like a agentic workflow to do research, in a sense, like we're just kind of like deferring that to the reasoning model, and then letting the reasoning model decide how to, take some of those steps, decide what to do next. So the architecture that we went with, so all the different sort of like attempts at emulating deep research by Hugging Face, Cohere, others, they'll have a different architectural diagram. It's just like a design choice. But ours has essentially like just two parts. There's the data ingestion, and so that could be data beforehand. So it could be like your internal docs, could be that could be like your, so in our case, I have indexed the entire zillets.com website. So that includes all of our, like product materials, the API documentation for the version that version that we host, as well as all the marketing sales material. It can also be crawled web pages, streaming data. So that part is data ingestion, and so just like a RAG or an agent application, what we do is we take that, we break it down into chunks, embed it, and then store it in our vector database for retrieval later on. And then, once we've done that, so in our case, for the sake of simplicity, all of our data will be ingested in advance. But, it's just sort of one step beyond that to add web browsing as a tool usage. So just imagine, so the user comes along, they have their query. So how we've designed it is the first step is we do a query decomposition. So we break down their query into a number of subqueries. So smaller questions that in totality can answer the overall question. And then that goes to a collection router. So a foundation model decides which data source from the data ingestion am I going to look up to answer this question, or potentially multiple. So it then performs the retrieval from Milvus, our vector database that we're using. And so that's performing semantic search. And so once we've done that, then I think this is sort of like the, key step here is we use the reasoning model to ask the question, to do some sort of like reflection, and ask the question, are there any knowledge gaps in the what we've sort of, so the subqueries we've decomposed the query into so far, plus all of the retrieved chunks. And then if it says yes, then we get it to generate additional subqueries, and we sort of keep going around that loop. But otherwise, the model can decide, no, I'm finished. I have enough information to answer everything. So I'm going to go to the final step, which is synthesizing all of those chunks into a final report. Before I sort of go into some code, I wanted to give you just sort of like a little, like show you what the output looks like. So Deep Searcher written in Python, it's open source as well. So you can go to our GitHub repo, just do a Google search for Deep Searcher. So here's an example of running the Python app on the query, write a report comparing Milvus with other vector databases. So the first step, it inputs the query, and then it does this initial step, which is breaking down the query into subqueries. And then it goes through each of those, decides which data source to route it to, and then performs the retrieval from the vector database. And you can see here, like it's retrieved 5 chunks from the vector database. And so I think it's like an additional step I didn't mention here, but they'll sort of be like a filtering, or I guess like a re-ranking in a sense, for each of those chunks that the vector search retrieves. We're also going to ask the reasoning model to say, is this chunk actually relevant to the question being answered? So, so vector search, very fast, but has kind of like, I guess like coarse accuracy. So it's often really beneficial to do some sort of like an additional re-ranking or filtering on top of that. Okay, so then it just sort of like repeats this action, repeats it for the second subquery, and then the third subquery. So you can see the subqueries at the top here. Retrieves the chunks, go through this cycle until it's answered or retrieved all of the information related to those subqueries. And then it does its first reflection and it says, okay, given the query, given the subqueries, given the chunks that we've retrieved and we've removed duplicates, are there any knowledge gaps? And if so, generate an additional 3 queries to keep the process going. So in this case, it says, yes, we haven't fully answered the question yet. So here's some additional subqueries. So what are the performance benchmarks of Milvus, et cetera, et cetera. And then it just goes through that loop again until it's answered. And, I'll just sort of skip to the final step. And then, so once it's gone through that second iteration, in this specific case, when it reflects on the search results that time, so now it's got all of the subqueries from the first iteration and the second iteration, plus all of the chunks, plus the original query. It says no new search queries were generated, so it thinks that it doesn't have any it's satisfied with the information that it's got to answer the question. And then it just goes to the final step, which is actually generating the report. So all of these steps, the like breaking down into subqueries, the filtering of the chunks retrieved from the vector database, the reflection and generation of the new subqueries, and the synthesizing that into a final report. All of that is just prompts that we've designed and we're giving to the reasoning model. And then when it generates the report, so it just sort of like qualitatively by the output, looks like it's doing a fairly reasonable job. It's like well structured introduction, sort of key sections that look fairly sensible. Yada yada yada. Conclusion at the end. So this looks like it's working, and it says conclusion: Milvus is a compelling choice among vector databases, noteworthy for its high performance, flexible deployment options, and strong community support. So I like to joke it's recovered the ground truth. Okay, so let's build it ourselves, or let's look at how you might sort of put together like a really simplified, some code that implements that core loop, but does it with like all of the bells and whistles of Deep Searcher. So, actually, I won't skip back. So I'm going to go across to Jupyter Notebook. Okay, and let's see. Oh, and by the way, so because of the lights, I can't really see anyone. But if you have questions and you want to stop me midway, just yell out, and happy to answer those. Okay, so I've got a Jupyter Notebook here. So the first step is, so to work with Milvus, we use, in this case, the Python client, which is called PyMilvus. So we just go and pip install that. And then, the most sort of like time-intensive, compute-intensive step here is actually forming the data. So offline, I've downloaded all of our website. So I've just like implemented like a simple crawler, crawls the sitemap, downloads all of the pages, converts them into Markdown, and then chunks them up. And this is sort of like a data set table, which we'll have a look at some of the rows in a second. But I've done all of that in advance. So if you want to sort of try along, test it out, or substitute this with your own data, you can just like download this or replace it with something with the same columns. Okay, just import some more libraries. So you can see I'm using Hugging Face sentence transformers for the embedding model in this case. And so for this specific example, I'm using one of OpenAI's reasoning models. I've also tested it with a version of DeepSeek R2 locally, and it seems like it's sort of the output is just as good. Okay, so we downloaded the file, the data. I saved it as a Parquet file. So that has, so it has 3 columns. So one column is the vector. So this is the vector embedding. I think it's something like either 300 and something or 700 something for this particular embedding model. Then we have the actual text itself that is the chunk that corresponds to that embedding. And it doesn't show it here, but there's a third column that also shows the website that chunk comes from. So we can, if we wanted to, we could do like a citation or attribute that chunk after the fact. It turned out I think there was something like 70,000 web pages. When I chunked that up, it's 312,000 chunks or vectors, which, is still like sort of fairly small scale, something that we can do on our laptop without any sort of like super complex indexing structures. Embedding this, I did this locally on a NVIDIA graphics card, and that just took a couple of hours to embed all of this, like entire website. So this is something that you could put together really quickly and really easily, and be like testing it locally. So if you wanted to replace that with your company website, or you wanted to, I don't know, you could like extract all of the data from your Discord or your Slack and put that in as well. Just sort of like substituting this data file with another one. So once we got the data, we're going to open up a connection to the database. And so we do that by creating a Milvus client object, which is inside this PyMilvus library that we've installed. We give it the name of the file we want to save to, and that's how it knows that it should be using the local deployment option rather than the Docker or the Kubernetes version. So if you wanted to scale up, you would just start one of those deployments and replace this URI with the IP address or the URL, and all of the other APIs are exactly the same. So you could very easily switch this across to like a distributed or a version that can scale up to tens of millions, hundreds of millions, even billions. Once we've done that, so now we need to just do like a bit of bookkeeping. So we create what's called a collection, which is essentially just like a table. So what a table is for a relational database, a collection is for Milvus. So we create the schema. This has got like a primary key and then just the 3 columns of our data set. And we also tell it to prepare a specific type of vector database index. And so in our case, we're just saying use the default for Milvus Lite, but you can replace this index type with any number of different indexing algorithms. So it could be there's HNSW is a popular choice. We also offer some sort of more scalable ones like disk ANN. So there's a few maybe a dozen choices for that. And we can specify the metric that we're using to measure similarity or distance in this space. And then we just create the collection. So we just call create collection with that information. And just to make sure it's done something, I'm just asking it to list the currently created collections, and it gives you default. So we've opened the database, we've created the table. Now we can actually insert our data. And so to do that, I just iterate over the records in this pandas table that we opened. So in this case, all of our data fits into memory. So I just loaded it into a pandas table. We convert it to a dictionary here, and then put that into calling Milvus client.insert. In batches, we can insert that. And then just to sort of make sure that everything's working, I show that after we've done that, our collection now contains 312,000 vectors or entries. So we've done the data ingestion. Now we can now we can do the query part. So the interesting part. So to do that, we need to open up the same embedding model as the one that we use to embed the data, which I know is this one here. So use Hugging Face's sentence transformer library for that. Then we can encode the query. So similar to before, the query is going to be comparison between Milvus and Weaviate. And then all we need to do is call this Milvus client.search to perform the similarity search on the vector database. And so we tell it what collection, the query vector. So as far as Milvus is concerned, it's just vectors in, vectors out. It's agnostic to how exactly these vectors are being produced. And then we tell it to limit it to 10 results, give it a few parameters, and then printing out the results. It's this list of these entries, and so just for debugging, I've asked it to give back the source, but when we're doing the actually building the loop, we'll be getting the corresponding text, of course. And so just looking at these URLs, they sort of seem like sensible URLs to have retrieved the text from, given the query. So the query was comparison between Milvus and Weaviate, and you can see these URLs seem like they're sensible. Okay, so as I mentioned before, all this is really essentially all we're doing is constructing various prompts and running them at different times to produce this agentic workflow. So we have the prompts defined in this cell here. So we've got the one that breaks it down into queries. So we do some in-context learning here. We give it an example. We have a re-ranking prompt. And so this prompt will just say, determine whether the chunk is helpful in answering any of the query questions. You can only return yes or no. So this is the filtering step that will take the results retrieved from the vector database and then say, filter out the ones that perhaps weren't such great, relevant results that were retrieved. And then I think this is sort of the core step, which is the reflection. So that's just asking it to identify if there are knowledge gaps in what it's retrieved so far, given the subqueries, and then if not, then break it down to additional subqueries, or else go and generate the final report. And then we have the final prompt, which is just telling it to generate the report. So very simple, 4 different prompts for different steps, and now we can actually implement the core logic of that loop in the architectural diagram. So in this case, I was using OpenAI, but as mentioned, I've also tested it with some local reasoning models, so a version of DeepSeek R2. So I've got a RTX 4090 graphics card, 24 gigabytes of graphics RAM, so that can run some reasonable models at home very quickly. Okay, so just testing out some prompt completions here to make sure that my API key was working. Now we can implement the steps in the second part of the architectural diagram. So we'll define the query. So the query is write a report comparing Milvus with other vector databases. We then use our subquery prompt, and we feed that to, so we're going to be using O1 Mini. So we feed it to this reasoning model, get the result, and then for this sort of like a pedagogical example, I'm using a few sort of hacks here. So instead of doing like, I guess like principled structured output, I know that the output from OpenAI will have a certain format, so I can just use some like basic string processing to extract the subqueries. But obviously, like if you're doing more like production system, or even like DeepSeek, our open source version, you would want to be prompting it to, like, maybe you want to say, okay, output the result in JSON, and then use an additional library on top to like ensure that the output is well formatted. Okay, so these are the subqueries in this case, and then after that we can define the main loop. So the main loop, it's going to loop as long as we have subqueries to answer. So for each, we can retrieve the chunks for these subqueries in parallel. So we encode them. That set of 4 subqueries. We get this query. It's a list of vectors. We then run the Milvus client search, and that retrieves chunks separately for all 4 of those subquery query vectors. And then for each of those, we different queries are very likely to have retrieved some overlapping results. So we make sure that our chunks are unique. I define the filter chunk, and then actually perform the filtering. So and you can see like how sort of like easy it is to. So I'm not using any agent libraries. I'm just sort of like doing this manually, and it's no sort of like need for any additional libraries on top of this. And then the final step in this loop is asking it to reflect. And so it gets the query, it gets the previous subqueries, and the previous unique chunks. And then we ask it to do that. Is there a knowledge gap? It gives back the response. And the again, just like a small hack here to break down the return result into a set of strings of subqueries. But of course, you would want to use some sort of like library, like outlines is a good one in Python to ensure that you're sampling from your foundation model with a guaranteed output format like JSON. Just some insight into what's going on. Just printing out some steps here. So when I run that, you can see it's going through these various steps. It is filtering out some, but not the majority of the queries. So, when I did look into this manually, it did seem like these were retrieved chunks that perhaps weren't so relevant to the query at hand. And then after reflecting, it says, no, I'm going to break it down to 3 additional subqueries, go through the same steps, do the reflection again, and in this case, it only wants to do 2 iterations, and then it can terminate. And then it can generate the report using that prompt. So this is essentially how deep the architecture of Deep Searcher is working. I've just implemented like a simplified version for pedagogical purposes. And then we'll take a look at the report. So I formatted the Markdown in Jupyter Notebook. So again, it looks like it's a well-written report, has like a reasonable structure, has like a sensible sort of like progression of the information, how like the order of presenting the information. You can see how it's used like the queries, the subquery breakdown to work out what sections to put in the report, although there's not like a one-to-one correspondence between subqueries and headed sections. And it can do things like, so presumably it found some table from the website in one of its chunks and was able to like insert that. So it looks like it's doing a good job of generating a reasonable report. And if you wanted to sort of, go a few steps beyond this, I think the next one would be implementing web browsing as tool usage. Although just sort of like playing around with it myself, I found that it can get very expensive very quickly. So, that's why, so deep research, it might take like half an hour or more to generate your results. It's launching a lot of web browsing requests in parallel behind the scenes, presumably. So, if you're OpenAI, that's okay. But on my local machine, not so feasible. So this is just like a really simple example of how easy it is nowadays, and literally within the last 3 to 6 months, with open source reasoning models, to actually build one of these agents. So very simple in architecture, but very effective in its output. And we did it. Aside from OpenAI's reasoning model, only using open source tools, which I think is really cool. So Milvus, open source, Hugging Faces libraries, open source, the embedding model, open source, the reasoning model. We could have replaced the OpenAI one with an open source one like DeepSeek R2, as I've done before, and then everything would be open source. So you can do all of this using open source tools locally on your machine, and get some like quite impressive results in my opinion. It's even like giving a sort of a call to action here, and providing some references at the end. If you want to learn more about that or sort of similar topics, we've got like a really good set of tutorials on the Milvus website. So go to milvus.io, and then in so here we've got tutorials, bootcamp, and we've got a number of really, I think, like cool tutorials how to build different things. So whether it's like a multimodal semantic search, a hybrid search combining vector search plus lexical search, some other applications. So vector databases not only useful for search, of course, but I guess perhaps like different types of search. So recommender system is perhaps just like a different type of search. show you how to do some cool stuff like GraphRag. Encourage you to check it out. But going back to the slides. Okay, so where to from here? So we built this like very simple but effective research agent from open source tools. But that doesn't mean that, there's not sort of like very serious challenges. And so here are sort of like three of the main ones, in my opinion. And I think like the main sort of challenge, it seems like this is the most important component in generative AI, is the data. And so how we can scale up that data collection, ensure that it's high quality. If we're actually training a reasoning model ourselves, how can we sort of obtain those multi-step reasoning traces that we then do the reinforcement training on the model. Like if you open AI, Anthropic, you can build these custom data sets, but it sort of like presents a bit of a moat to hobbyists and small startups. So I think like a big challenge is always building really good, high quality open source data sets for what we want to do in generative AI. So the second one is the cost. So OpenAI's deep research, very, very impressive, but it's very, very expensive in terms of inference to run. And so I think, if I'm not mistaken, I think you need to be like on their pro plan, $200 a month. But I still think, so from what I've heard, like that's not covering the costs of what it takes to run this model. So these research agents, they have to launch, they have to do a lot of foundation, a lot of LLM inference. You can see that each of those steps in the agent did a call to the LLM. For reasoning models, it's perhaps like more costly because they're often going to sort of like vary the amount of computation they do according to like how their reasoning goes. Like I think typically sort of consuming more tokens or generating more tokens for a particular prompt than just like a plain non-reasoning LLM. How are we going to sort of like get around this cost? Well, this isn't like unique to research agents. I think one answer is going to come from specialized hardware. So there's a lot of startups working on hardware that is specialized. So, GPUs originally designed for crunching matrices for computer graphics, but they're obviously not specialized for doing inference on transformer algorithms. So I think like a big sort of factor in sort of decreasing the cost is this specialized hardware that companies like Samba Nova are developing. I think the second one is algorithmic improvements. So I think it's something that's like overlooked. There's always like, it seems like each month, like new developments in how we can more effectively quantize our foundation models for very little or minimal degradation in the performance. So it's things like quantization. There's sort of like, I guess, like surprising innovations, like when DeepSeek released their reasoning model earlier in the year. So who knows what the algorithmic improvements are going to be. It might be sort of, people are working on architectures beyond transformers. So maybe like one of those will become the like the dominant way of doing things. And then I think there's sort of like, so I guess sort of like overlapping with those is the issue of scaling. So, and just like scaling more generally. So once we've built this research agent, how are we going to like scale it up data-wise? How are we going to store all of these vectors from what we've ingested? I think this is a good segue to some of our offerings. So as I mentioned, we have Milvus, the self-managed version, fully open source, adopted by a lot of big companies. But we also do a fully managed version. So running a Kubernetes cluster, it can be kind of complex. Many startups don't want to do that themselves. So we also have a fully managed service, Zillits Cloud, which also has a lot of additional features. So same API, but additional features, including a proprietary vector indexing algorithm. And then perhaps you don't want to manage it yourself, but you also can't sort of, offsite all of that management because of maybe it's like privacy concerns. So in that case, we have a third offering, which is bring your own cloud. In that case, you can bring your own private VPC, whichever cloud service you're operating on, and you can have sort of like the best of both worlds. But in any case, you set up once, you might start developing on Milvus, get your prototype working, then decide, actually, I don't want to manage the service, so I'll switch across to Zillits Cloud, but you don't need to change any of your code because it has a common API across all of these products. Hopefully, learn something. Definitely encourage you to check out Deep Searcher on GitHub and play around with it. Extend it. Send requests, some PRs. Would love that. And let's stay connected. So again, I've got my LinkedIn here. So really love connecting with people on LinkedIn. Also, we do like a free weekly one-on-one office hour sessions for Milvus. So you just sign up. I got a QR code for the link there. And you can then schedule a time to speak with an engineer one-on-one to help you sort of overcome your productionization issues. So I think with that, my time is up. So thanks everyone for your attention, and hope to connect with you later in the conference.
Thank you, Stefan. Do we have any questions? Let me walk up here. We don't have a whole lot of time for questions, but we can take a couple.
So I did notice there was a limit in there. I was curious if you ask a question that's just way outside the corpus of data, like, how do you find a good banana? Does it eventually give up on researching and give you a generic LLM answer? Does it time out? Like, how do you handle that use case?
Sure. So great question. So obviously, like a production system would have additional things like guardrails, but also some sort of like limits. This hasn't really come up in the sort of testing I've done, but in Deep Searcher, it has like a fixed number of iterations. So I think it's something like, you can set that, maybe the default is like 3 to 5. It's not just going to keep going infinitely. And then I think also like you probably want to set like a token limit on your calls to the reasoning model as well. So all of those are parameters that you can control in Deep Searcher.
I would imagine it would eventually like just pull in the entire website and then run out of tokens for the...
That's what, so you might think that, but the reasoning model, it's actually, just like the way it's trained, the fact that it's, trained on web scale data plus the reasoning training as well. It does a really good job of working out, okay, I'm going to stop here because I've got enough to answer these questions. So I think if the model were different, it wouldn't work as well. You definitely have to use a strong reasoning model for it to work properly.
Okay, thank you. I think we have time for one more question, and then we're going to go to the next room for Q&A.
Ask me anything.
Yeah.
Thank you. Interesting. Your data set was pretty well defined and trusted. In a lot of research applications, there's a credibility component of the data that's available.
Yeah.
Can you comment on that and how you might amend this to handle that kind of situation?
Yeah, sure. So, well, I think it sort of becomes a much more challenging problem when you also have to ask the question, is my data actually factual? So, I can sort of like speculate on what some other systems, more complex commercial systems like Perplexity, ChatGPT do. So I think, in this case, you're working on your private data, so it's not so much of an issue. But if it were an issue, I think you would definitely have to design like extra steps into this workflow, additional prompts. Maybe you would be looking at, does like information across various sources corroborate each other? How you can ask it to rate the trustworthiness of different sources. So I think that would just be, again, like, additional prompting, additional steps, a bit of sort of like, common sense engineering, but definitely a much more challenging problem to solve.
Thank you.
Okay, thanks everyone.